All right, this is Tuesday, June 29th, 2021, Math 3 spring term. Just class notes and lectures trying to strengthen our understanding about half-life, compound interest, continuous interest, natural number E, irrational number E. All right, so that's what we're going to try to be doing today. To start off, a revisit about half-life. And for half-life, the story is it's the amount of time it takes for half of a substance to disappear. But the trick is you're always starting from the amount that you have at the end of a cycle as you calculate how much you have left at the end of the next cycle. And if it's not an integer number of cycles, well, then that's why you have a calculator. So the idea of half-life is if I start with, let's start off with our, 200 units of something, ounces, grams, milligrams, whatever it is, pennies, 200 pennies. Let's say that every day that you come to class, I'm going to take away half of your money every day. So you come to class today on Tuesday and you have 200 pennies with you, and I take away 100 pennies. Gone. This is, my form of payment here, I guess, bribery. So for bribery, actually, I don't know how to spell bribery since I've never engaged with it. Let's just call it the mafia. Great. So I know how to spell mafia, but I don't know how to spell bribery. I just can't spell mafia so that it looks like an F. M-A-F. It's the name of the bad guys. And so you start with 200 pennies and you come to class and the mafia takes away, so you have 100 pennies left over. Great. Well, the next day you only bring what you have left over. You don't get any new money. So you come to class with 100 pennies and the mafia takes half of those. It takes away 50 pennies. And that leaves you with 50 pennies. And then the next day you come to class, now you only have 50 pennies. And the mafia takes away half of your money. And so you're left with just 25 pennies. Next day you come to class, you only have 25 pennies. And here's where we have to talk about, well, are we going to deal strictly with integer numbers, or are we going to mathematically deal with half pennies and quarter pennies and thousandths of pennies? In the real world, when we are applying the half-life formula to something in the real world, generally we can deal with numbers that are so vast that, yes, we can have a thousandth of a unit of something. A thousandth of a milligram is still lots of molecules. A thousandth of an ounce is still lots of molecules. And usually it's the molecules levels where these half-life changes are occurring. So in my example here with pennies, if we're going to be proper and stick with pennies, the mafia has to take either 12 or 13 pennies. And being the mafia, we'll say that they take 13 pennies. So they're rounding up. Instead of taking exactly half, they're taking 13 instead of 12.5 pennies. And that leaves you with 12 pennies. Next day you come to class, you have 12 pennies. The mafia takes half of them. And so you're left with 6 pennies. Next day you come to class, all you have are 6 pennies. The mafia takes away half of them. You're left with 3 pennies. The next day you come to class, you only have 3 pennies. Once again, it's an odd number. So when you cut it in half, is the mafia going to say, oh, we took half a penny last time. We'll be kind to you. This, no, you guys, you're good. You're good. We'll only take one. No, it's the mafia. They're going to round up again. And you're left with, they're going to take away 2 pennies. And I see, you can't actually see a single thing that I'm writing, can you?
No.
Nice. I should just delete all that and start all over. Oh well. And I didn't pick someone to take care of things for me today either. Oh, that's too bad. It was a great story. Too bad you missed it. I'm waiting, I'm waiting, I'm waiting. There. So this is what I wrote. Too bad. Well, you've heard the story. Starting with 200, if I remove half of it every day, then we would say the rate is 1/2 per day. Your rate is you lose 1/2 per day. And here's the columns that I was scribbling down that you missed. Starting with 200, take away 100, you get 100. Next day, you come in with only 100, you lose half of it. Next day, you come in with 50. Next day, you come in with 25. Next day, you come in 12. Next day, you come in with 3. Now you've arrived with just 3 pennies. And the mafia being who they are, they're going to take 1.5 pennies rounded up. So they're going to take away 2 pennies. And now you have 1 penny left. With your 1 penny, they're going to say, "Oh, how nice of you," and end of the analogy. So this is an example of how Half-Life applies as a kind of made-up example, where in whatever the unit of time is, so the half-life time would be 1 day, and really school days at that, right? This takes several days to go through all your money. What if you started with twice as much money, 400 pennies instead of 200 pennies? That would add 1 day to how long this goes on. What if you were to double that again and start with 800 pennies? Well, that would add just 1 more day on top of the 400 pennies. So doubling it day after day after day doesn't buy you a whole lot more time for this to go on before it gets down to really teeny tiny numbers. All right, so that's the point I was trying to make about Half-Life. Applying it to a problem, well, your math skill should be the amount that you end up with is equal to the amount that you start off with times 1/2.
Mr. Turk, did you mute yourself?
Did I mute myself? No. But I will look here if Hong Gosh. Nicholas, can you hear me? It says my mic isn't working. All right, well. Testing, 1, 2, 3. Can you hear me? Nicholas, can you hear me? Okay, so then I guess the question is, can I hear you? Testing, 1, 2, 3. Nicholas, can you hear me?
Yes, I can, Mr. Turk.
And I can hear you. So I had a microphone failure on my first piece of equipment. I wonder if that means it can't record anything now. Probably means I can't record anything now, too. Nice. So I really should repair that before we move on with today's fun-filled, exciting lessons. If it comes back on, then I have to shut the other microphone off. It wants me to reload the page, so I might actually leave the meeting for a moment. We'll see. Yep, I've left the meeting. This is nice. Not really, I'm being sarcastic. Rejoining. Shutting off mic. Turning on mic. Testing. Testing. Nicholas, can you hear me now? Okay, I cannot hear you. I guess that's the problem. Now, Nicholas, can you hear me now?
Yes, I can.
Okay. Meanwhile, let's set up about the wheel of names, something I didn't take care of. Should have done that when you students were first walking in. Oh well. As I go through summer school, I'll figure this out and be more efficient. Right now, this is terribly inefficient. So let's get rid of all of those names and put in. It's loading. It's loading. I guess you still can't see it. Okay. Don't worry about it for the moment. I will fix this momentarily. That would be this button. And James, since you shut off your camera, well, there goes your points. Okay, huge waste of class time. Sorry. I wanted to try to work some more problems with Half-Life because you students, some of you get it and some of you just could use some more reinforcement. So it's t raised to the number of half-lives. So simple examples. If I start with 200 pennies and the half-life is 1 day, then for every day that goes by, I take away half of what I started with. That's great. But what if it's not a full day? What if it's just 3/4 of a day? What if it's half a day? In that case, you don't know how much to take off until you plug it into the formula. So for right now, we're going to let A0 be 200 units again. And this time, we're going to be allowing it to be cut in pieces. So instead of pennies, it's going to be grams of sugar. And the half-life, I'm still going to leave it at 1 day, meaning a 24-hour period of time. And I say, okay, well, suppose instead of 1 day going by, I only let 7 hours go by. See, that's nasty. That's not even something that's 1/4, where you could like hope to do it in your head. And the point is, you have a calculator. You don't need to do it in your head. What you can do is plug it into the formula. That's what calculators are for. So for A0, you would type in 200, in this case, grams. 1/2 is 1/2. And we have to turn the units into the same units. So if this is units of days and that's units of hours, you have to make them the same. It's easier to turn days into hours than it is to turn hours into days. Because to turn hours into days, you need a calculator and it's going to be some fraction. To turn a day into an hour, it's very easy. It's integer. So what we're going to do is put it from days into hours. Well, which one goes on top? One of you made the mistake on your homework. You put the half-life time on top. No, it's the amount of time that's gone by that goes on top. So 7 hours goes on top, and 24 hours, 1 day converted to hours, goes down below. Now, when I say down below, all of this is the exponent. So the exponent in this situation is a value less than 1. Fortunately, your calculator can handle a situation like that. So you turn on your calculator, go 200 times 0.5 raised to the open parentheses 7 divided by 24 close parentheses, enter. Doop, 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 beep, beep, beep. And the calculator says, oh, in this case, it's 163.3915453. I'll just round it to the nearest gram and say the answer is 163 grams. You cannot get that by using a straight line. Your straight line would have said, oh, in the first 24 hours, we take away 50 pennies. Yeah, it's not a straight line function. It's an exponent. So you have to use your calculator to work out solutions for something like this. All right, so do you have questions about this so far? This is Half-Life, where time is given and the initial amount is given, and you only need to figure out the final amount. Okay, well, what if I give you the final amount and the initial amount, and I ask you, no. I give you the final amount and the amount of time that went by, and I ask you, so how much did I start off with? Okay, so that's a new problem. And that one would be, let's say that my final amount is, let's say 37.2 grams. And that the time that has gone by is 6.2 days. And I want to know, stop that, what was the initial amount that I started off with in this situation? Now, this is a new one, right? I just made up the numbers. How do you solve for the initial amount? Well, the formula is the amount you end up with is equal to the initial amount times 1/2 raised to the time divided by the half-life time as the exponent. And we're still using a half-life time of 1 day for this example. So that means the only thing that's unknown is the initial amount. Everything else is known. So what do you do when you have one unknown? You isolate it and you solve for that one unknown. So this one unknown, the initial amount, is equal to the amount that we have left divided by 1/2 raised to the t over t 1/2. And just plug everything in on the right-hand side. That means you're plugging in 37.2 grams divided by 1/2 or 0.5 raised to the 6.2 power. Because the half-life is 1 day, 6.2 days divided by 1 day is 6.2. Handy dandy calculator can handle this one too. 37.2 divided by, I would do this as 0.5 raised to the 6.2 power, enter. Beep, beep, beep. And I get the initial amount for this made-up situation was 2,734 grams. And because you students are knowledgeable about Greek prefixes, you recognize that would be 2.73 kilograms to 3 sig figs. Because after all, what is a kilogram? It's 1,000 grams. All right, so there's an example of how you would solve for initial amount if you knew everything else. Of course, time is the one thing that we usually don't know. We know how much we started off with. We know how much we currently have, but we don't know how much time went by, but we also do know the half-life. And so that's where radioactive decay comes in. For example, the half-life of carbon-14 was 5,730 years. We're not making that up. This is what we've measured and determined. So what if I know that I start off with, 2.73 kilograms, which is a lot of carbon-14, right? I should really make it 2.73 milligrams would be a more realistic value. So let's do that. Milligrams, thousandth of a gram. And I go measure it, and I say, okay, I know that's how much we started off with thousands of years ago, or maybe 10 years ago, maybe last week, whatever it was. And now I'm measuring that I measure how much there is right now, and I see it's 0.732 milligrams. And I know what the half-life is. How do I turn this around and solve for T, that unknown mystery amount of time? Well, the formula hasn't changed. The amount that you have now is equal to the amount that you started with times 1/2 raised to this unknown mystery amount of time, right? I'm going to call that X for now. See, that's the one thing we don't know. Let's call that X and go solve for X. So solving for X, the first thing I would do, or next thing I suppose, is divide both sides by the initial amount. And so that means on my calculator, because I'm going to do it that way, 0.732 divided by 2.73. So on the left, I have some scary looking number, 0.2681. Okay, what is that? That is 0.732 grams divided by 2.73 grams. Okay, so that's where that number came from. This is that. On the right, I now have 1/2 raised to the x power. And I don't know x. I'm trying to solve for x. This is an exponential function. The way to find x is to make use of logarithms. Okay? That is the beauty of using a logarithm in this situation. And the property that we're going to use of logarithms is that any number raised to some exponent, when you take the log of it, that is equal to x times the log of that number. Okay, so that is the property we're going to use. And what we do to one side of an equation, we have to do to the other side of the equation. So if I'm going to take the log of the right side of the equation, I must take the log of the left side of the equation. And so this thing now looks like the log of 0.2681 is equal to, I'll do this in one step, x times the log of 0.5. Or if you like, you can write it as 1/2. Well, then, now, you can divide both sides by the log of 1/2. Perfectly allowable. And this gives us the value of x. But to get the actual value, use your calculator. So I'm going to plug in, calculator, what is the log of 0.2681 divided by the log of 0.5? And it says, oh yes, that result is 1.899156876. And I'll round that to 3 sig figs and call that 1.90. That is the number of half-lives that have gone by. Because I set x equal to the amount of time that's gone by divided by the half-life of carbon-14. So now, at last, I can solve for the amount of time that has gone by. I take the half-life time of 5,730 years, and I multiply it by 1.90 half-lives. So here we go. This number times 5730, enter, beep, 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 and it says 10,000, almost, I'm going to round it up, 10,900 years have gone by in this example. Ta-da! Just for your educational benefit, where does this carbon-14 come from? So you live on planet Earth, and the Earth is surrounded by an atmosphere shown not to scale. The atmosphere contains carbon-12 as a naturally occurring isotope, but there are cosmic rays hitting our atmosphere from outer space, and they're coming from all directions. And some of these cosmic rays generate the radioactive isotope carbon-14. All life forms on Earth, all aerobic life forms on Earth, consume oxygen from our atmosphere. As we breathe, we're also exhaling carbon dioxide. Through photosynthesis, plants are converting carbon dioxide in the atmosphere into sugar. Okay, well, that's sugar, C6H12O6. There's the carbon. As long as you are eating and breathing the air on Earth, you are ingesting the carbon-14 radioactive isotope that is present in our atmosphere, being replenished from outer space. Now, we believe that the rate of replenishment is a constant. If it was actually changing a lot, then our values could be off. But we have no reason to believe that it changes a lot. So, assuming that the rate of carbon-14 being ingested into our atmosphere, into human life, into life forms on Earth, is a constant rate, it's when you stop breathing, when you stop eating, that this decay process begins. And so that's what starts the clock of decay. And when we go analyze a piece of organic material, that's like a piece of tree, a plant, some clothing, a human remains, we measure what is the amount of carbon-14 remaining. We know how much you start off with and solve for time. And then we can say, oh yeah, this parchment paper really is 6,000 years old. Ta-da. All right, so that was part of one of the homework issues you had last night. Another big issue deals with compound interest. So let's go over that one again. The formula for making money, basically, is the amount of money you have over time is equal to the principal amount that you start with. So I'm going to use P for principal today. And that is going to be times the amount that you put in, add to that the interest rate. Now, interest rates are generally expressed as a percentage per year. But what if you compound your money? Okay, so that's where K comes in. K is the rate at which money is being compounded. Destiny, you are rejoining. Nice. Okay, now all of this is over time. And some of you did this homework correctly, but many of you missed out that it's the exponent is the total amount of time that goes by. And you express the total amount of time in the number of compounding cycles that take place. So, for example, if I tell you that the interest rate is a generous, let's not use numbers that are like the homework, a generous 8% interest, and is compounded annually. And I invest, 3,000, what was that number? Well, let's make it 3,000 $1,720. 1 year later, I will have 8% more than I started with. So that's what it means to accrue money. Accumulate money. And the idea of putting it into a bank or investing it in stocks and bonds and real estate and everything else is that after it's gained that much money, you then put that into your principal and start over again. So it's not 8% and then 8% and then 8%. It's 8% and then 8% of your new amount of money, and then 8% of the new amount of money after that. So using a calculator, if I say, what is 8% of 3,720, that would be 0.08 times 3,720. 8% of this amount is $297.60. Okay, so after 1 year, you would have that much interest, and you add that. This is the part maybe you didn't understand so well. You add that to your principal, the amount that you started with. So now here's your total amount of money. Oh, what did I do wrong? I misadded because I didn't look at the columns carefully, right? So I have 60 cents. I have 7 plus 0 is 7. 9 plus 2 is 11. 7 plus 3 is 10. And I have $4,000, $4,017.60. Ta-da! That becomes your new principal the next time around. So you're not starting off with $3,720. No. Now your new principal is almost $300 richer. And so you have to put that in and say, what is 8% of that? 0.08 times 4017.60. And it says, oh, your new interest is going to be $321.41. Now, there is a programmer who years ago would take the 0.08 pennies and put it into his own bank account. And because all the customers were using his software for many banks, he made lots of money until he got caught and went to jail. This is what we mean by interest rates and compounding. Now here, we're only compounding it once per year. If it's compounded every 6 months, oh man, life gets better. So let's see, this is after 2 years. What's the total amount of money that I have now? So 1, this becomes a 10, 7, 8, 9, 3, 3, 4. So at the end of 2 years, if it's compounded annually, I will have $4,339.01. But if I can compound it every 6 months, oh my goodness. Then starting off with 3,000, I can't write, can I? I can't erase either. Okay, so if I start off again with $3,720 and it's compounded twice per year, that 8% interest rate, when you divide it by 2, becomes 4%. So this becomes 0.04. And you're going to raise it, you're going to compound it twice in 1 year. So each year, this is going to be squared. That means at the end of the first year, $3,720 times 1.04 raised to the second power. Beep, beep, beep. So what this does is it doesn't calculate the interest, it calculates your total amount of money. And the total amount of money after 1 year is already $4,023.55. Okay, so compare that with $4,017, and you see you've made $5 more than the $321 you would have made. And of course, what would it be like after 2 years? Well, after 2 years, this number would be 4 instead of 2, because 2 years has 4 periods of 6 months. So if I go 3,720 times 1.04 raised to the fourth power, oh my goodness, I'm rolling in the dough. I have $4,351.87. Compare that with the measly stinking $4,339, and you see, oh, this time you made about $6 more, not just $5 more. I'm rounding. So the more frequently it's compounded and plowed back into your principal, the better off you are as someone who's trying to make money. All right. This is about all that I want to cover by way of debriefing you on the homework from last night. What I want to do when we get back from our 3-minute break is introduce you to the natural logarithm if I can, and certainly deal more with exponents, dealing with what's the domain, what's the range, what is there an asymptote, what does that mean, where is it if there is one. Okay, so let's go ahead and start our 3-minute break now. Now's a good time.